Welcome back to the next video, everybody. Today we're finally going to be able to prove proposition 4 after several videos of work, assuming a couple of things that we'll prove later. So that proposition, I'll invite you to go back and check, is on comparing the size of the congruence modules eta sub sigma as sigma grows. So let's get into this. We'll let sigma prime be in sigma sub rho bar. That'll be a finite set of primes containing a given fixed set of primes sigma as usual, by the corollary at the end of the previous video, and I would invite you to go back and check that out. Proposition 4 will follow by simply comparing the determinant of A and the determinant of A prime, where A prime is the matrix formed by considering the set sigma prime, whereas A was formed by considering the set sigma. Okay, so I'll let you go back and check the details on the matrix A. By proposition T sub m applied to sigma prime, there's an isomorphism between T sub sigma prime and T prime sub m prime, where m prime is some maximal ideal of T prime sub O, which is T prime sub Z tensored up to O, where we have T prime sub Z acting on S2 gamma 0 n sub sigma prime. We'll let P prime denote the preimage in T prime sub O of WP prime, and we'll let M prime equal n sub sigma prime just for brevity. We'll let X prime be X naught of N prime, and J prime be the Jacobian J0 of N prime as usual, again for brevity, and we'll define self-dual T prime sub M prime modules L prime sub T and L prime sub H, just like we defined L sub T and L sub H before, okay? In the case where sigma prime is sigma union sum prime P in sigma sub rho bar minus sigma, we'll define a homomorphism that we'll call phi sub T from L prime sub T to L sub T of T prime sub M prime modules. To do this, we'll first assume that P isn't L, the fixed prime that we've been working with, so that N prime is just NP squared by definition. And we have a surjective homomorphism from T prime sub M prime to T sub M induced by the map from T prime T sub sigma prime to T sub sigma defined by TQ maps to TQ for Q not equal to P and TP maps to 0. Now, there's these maps from the upper half plane H to itself given by T maps to T, so the identity map, tau maps to P tau, and tau maps to P squared tau. These induce maps alpha, beta, gamma, we'll call them, from X prime to X, these modular curves. And these, by functoriality, in turn give rise to a map from J prime to J cross J cross J. Here's the map. It sends X to alpha lower star X, beta lower star X, gamma lower star X. All of this stuff was defined back in chapter 3, these lower star maps. And this itself induces an O-linear homomorphism from the Tate module TLJ prime tensored up to O over Z sub L to TL of J tensored up to O over Z sub L cubed. Okay, so this is all information we've known for a long time. Let's compose this map with the projection to L cubed sub T, which is the Tate module TLJ tensored up to O cubed localized at M. And we'll follow this by the map L sub T cubed to L sub T given by the matrix 1 comma negative P inverse, T sub P, P inverse. This isn't completely unmotivated. It comes from the fact that G prime equals alpha upper star minus P inverse beta upper star T sub P plus P inverse gamma upper star G, where G is the eigenform associated to P that we built out of F before, and G prime is the eigenform associated to P prime that we built just this video. Okay, so there's a kind of a relationship between these two special new forms as we move from sigma to sigma prime. And here's the relationship. Well, this guy out front here is where we're building this matrix from right here. Okay, so we're going to need the following lemma. It says the composition from TLJ prime tensored up to O to LT is T prime O linear, where we can regard LT as a T prime O module via the surjection from T prime O to T prime sub M prime to T sub M. Okay, this is not hard to prove at all. It follows immediately from the fact that the corresponding map on Hecke algebras is just the following. So we go from T prime sub O to T prime sub O bracket U mod the ideal generated by F of U. That map just sends T sub P to U. Then we go from here to T localized at M bracket U mod F of U. That map is just the map sending U to U. And then we go from here to T localized at M just by sending U to 0. Okay, that's the corresponding map on Hecke algebras. Well, okay, so we have T prime O linearity then. What is F of U here? It's just U cubed minus TPU squared plus PU. It's kind of our characteristic polynomial looking equation here. Okay, so it follows from all of this, essentially, that TLJ prime tensored up to O to LT factors through L prime of T. Okay, and so that gives me my homomorphism that I've been after for this whole video. It's a homomorphism of T prime sub M prime modules that we'll call phi sub T, and it very simply goes from L prime sub T to L sub T. Okay, now this is the construction when P isn't L. When P is L, the construction proceeds similarly, except that we only have 2 copies of J instead of 3. And the map L sub T squared to L sub T instead of L sub T cubed to L sub T is given by the matrix 1 comma negative alpha inverse sub L, where alpha sub L is the unit root of x squared minus TLx plus L equals 0, as per usual. Okay. Other than that, it pretty much goes through the same, and you get another homomorphism like this. If sigma and sigma prime in sigma rho bar is arbitrary, because remember, these constructions really only work if you're assuming that sigma prime is sigma union one other prime p, but sigma prime could have multiple additional primes in it. That's okay. If you have an arbitrary chain of groups, sigma groups like this, the primes, then you just define phi sub t to be the composite of the maps given kind of prime by prime as you add 1 prime at a time to sigma. Okay. You can easily show, by the way, that this construction, in the case this is arbitrary, is independent of the choice of the ordering of the primes in sigma prime minus sigma. Okay, of course, you have to make sure of that, because a priori, these compositions that you're going to make here, if you reorder the primes here, you'll take a different composition of maps, and you could get a different output phi sub t, but that doesn't happen. Okay. All right, now we're going to need a map phi prime sub t going the other way, and we'll just define that to be the dual map that goes from L sub p to L prime sub t. Now let's define a map phi sub h from L prime h to LH to be the adjoint of the map phi prime sub h that makes the following diagram commute. Okay, so we're essentially looking at this upper map here. Okay, so this is going to be my phi prime sub h, and phi sub h will just be the adjoint of it. What is this commutative square? These vertical maps here, so we have maps from H1XO localized at M to O homomorphisms from LT to O, and then the same thing with primes, so H1X prime O localized at M prime to O homomorphisms from L prime sub T to O. These are just the isomorphisms that we have by definition of the LH and LT modules, okay? And then what is this bottom map here? This is just the dual map to phi sub T, okay? Okay, so let's keep going. We're going to need one more result that we're going to have to postpone the proof of until we finish the proof of proposition 4. I'm going to call it lemma Ihara, and it very simply says that phi sub t and phi sub h are surjective. Okay, if you give me this, I can prove proposition 4 now. Again, for simplicity, let's suppose that sigma prime is just sigma union 1 prime p, where p isn't L. If you unravel definitions, you see that the following diagram commutes. So here's the diagram. We go from h1x naught o naught bracket p naught to h1x prime o naught p prime naught. Then we go down to LH and to L at prime h on the left and the right respectively. And then we have this phi prime h map on the bottom that we just defined. Okay, the only thing I really have to do here is tell you what this top map is. The top arrow is alpha star minus p inverse pi of t p beta upper star p inverse gamma upper star. Okay, if we extend scalars all the way up to c, this map here, it sends omega sub g to omega sub g prime, and omega bar sub g to the c to omega bar sub g prime to the c, where g prime was defined just above. Okay, and these omega guys, these are our differentials on our modular curves, and c is complex conjugation. Okay, so you have this in the case p isn't L. What if p is L? The same thing holds if O naught is chosen a little bit differently. You just have to choose it to contain pi of A sub L, which is alpha sub L of G prime. And then the top arrow changes a little bit as per the discussion we just had above. You don't get this. You get alpha upper star minus pi of alpha sub L inverse beta upper star. Okay, so we have a commutative diagram kind of in either case. All right. Now, the commutativity of this diagram allows me to conclude that if xy is a basis for h1 x o naught p naught, so that is that upper left corner here, and the matrices A and A prime are defined using xy and phi prime sub hx, phi prime sub hy, respectively. And by the way, this is a basis because by lemma Ihara, phi prime sub h is injective, and h1x prime o naught p prime naught is two-dimensional. The commutativity of the diagram, again, if you just kind of read it the right way and unwind definitions, really just tells you that A prime is nothing but A, if you choose A and A prime relative to these bases, okay? Well, perfect, because now proposition 4 now just follows immediately by the corollary from the previous video. Because if A prime is A, then everything in the expression for the generator of eta sub sigma is the same as everything in the expression for the generator of eta sub sigma prime, except for one thing might be different: the L sigma sim squared pieces. Okay, but you can just write down the definitions of these explicitly and see how they compare to each other. See, like before, we had to worry about how these might look different from each other, which we could just write down and observe by writing down the definition of this guy. But then we also had this A and this A prime in the denominator of the expression for the generator of eta sub sigma, and we didn't know how those compared to each other. Well, it turns out they're just equal. Okay, and so now to prove proposition 4, which looks at how congruence modules grow as sigma grows, you just have to compare these, but you can just write down these by definition and see that they differ exactly as you need them to. And proposition 4 follows. So I will not write down the details there. That's just a go do it kind of thing. So proposition 4 is finally proven. So we understand now how eta sub sigma changes as sigma grows to sigma prime. And then we are short a couple of things. I think we're short lemma et hara as of this video. And then there is one other lemma we have to prove, which I will prove in a coming video. And then we will have basically gathered all the tools we need together to prove R equals T in the general case, finally. So happy holidays, everybody. Merry Christmas, Happy New Year's, all that stuff. I'll see you next week. Thanks for watching.